Welcome back to the Deep Dive. Our mission today is to take your stack of sources, articles on computational models, psychological debates, and uh, cutting-edge neuroscience, and really map the machinery of the human mind.
That's a great stack.
It is. We're
Yeah.
moving between these two worlds, really. The world of engineering intelligence and the world of trying to solve the enduring mystery of how our own minds manage information.
That's a perfect framing because the source material presents this phenomenal tension. On one hand, you have computer scientists designing intelligence with these rigid, detailed blueprints. They call them cognitive architectures.
Right.
And on the other, you have cognitive psychologists who are trying to understand probably the most hotly debated, messy, and limited component of human thinking, which is working memory.
So we're diving deep into
Yeah. What?
the theoretical construction of an AI agent, and then also decades of debate over what we call the workspace of the mind.
Exactly. And that's what's so fascinating.
The genius of these sources is how they bridge that gap, I think. We get to see how these high-level concepts like self-regulation or a temporary workspace are just essential for building a functional AI.
Uh-huh.
But then at the same time, you realize that scientists still can't agree on the exact definition or the capacity or even the location of those exact same functions in the biological brain.
Precisely. So our journey today is structured to move from the abstract, the theoretical architecture of an AI agent. We'll unpack a specific model called Karina.
Okay.
Then we'll shift to the three major and competing psychological frameworks that try to explain how we actively process information.
And finally, the brain itself.
And finally, we'll dive into the underlying neural evidence that's really starting to change how we define cognitive capacity itself.
It sounds like we need to understand the blueprint before we can appreciate the chaos. So settle in, because the key concepts we're threading together are metacognition, cognitive architecture, working memory, and of course, the ever-elusive nature of capacity limitations. Let's start with the ideal, the computational blueprint. So when we talk about a cognitive architecture, we aren't just discussing, some new AI that can write a decent essay or classify photos.
No.
We're talking about something far more foundational. What is the grand, ambitious goal here?
The goal is holistic intelligence. A cognitive architecture is essentially a foundational blueprint. It's a proposal for how to design and implement an artificial entity that's capable of intelligent behavior in a complex real-world environment.
So like the operating system and the hardware config for an AI agent.
That's a great way to put it. And crucially, this blueprint specifies all the necessary components and the structure, the architecture, that has to remain stable over the system's entire lifetime.
So it can learn new things without being fundamentally rewritten for every new task.
Exactly. Unlike a narrow, specialized AI, these cognitive architectures are pursuing a full general theory of intelligence. They're trying to bridge artificial intelligence and cognitive science by attempting to implement theories about human minds in silicon.
That's the key differentiator then.
Yeah.
They're explicitly built based on research into human cognition.
Yes, and they aim to exhibit comparable, broad behavior learning, planning, memory, self-correction, all of it. And this ambition leads directly to the next essential concept, computational metacognition.
That's the idea of the AI not just doing, but reflecting on its doing. I love the source's description, reasoning about reasoning.
It's the essential definition that creates this kind of dual-level system. Computational metacognition is this area of AI that focuses on giving intelligent systems the ability to monitor and control their own learning and reasoning processes.
Okay.
So it explicitly distinguishes between two major tiers. You have the object level, which is reasoning about the world.
The day-to-day stuff.
The day-to-day stuff, yeah. And then you have the meta level, which is reasoning about the reasoning process itself. A good metacognitive architecture provides a framework that specifies the structures and the precise relationships between these two tiers.
What's something we humans struggle with every day, knowing how well we actually know something. Let's use the architecture in our sources, Karina, as a way to visualize this. What are the modules of Karina's object level? This is the agent acting in the world, right?
Right. The object level handles the immediate interaction and the core cognitive stuff. It starts with the input-output interface. You've got sensors and actuators that interface with the environment.
Standard?
Pretty standard. Raw data moves to sensory memory, or SSM, which is this initial super brief buffer. Then it's processed by the perception module. That perceived info is then selectively passed into the core temporary workspace.
Which is our working memory.
Our working memory, WM, supported by attention. And all of that, of course, connects to the deep storage. So W is interacting constantly with the long-term memory stores, or LTM. And Karina models this using the traditional psychological breakdown. So you have procedural memory, PM.
The how-to knowledge.
How-to knowledge, exactly. Motor skills, activities. Then you have semantic memory, SM, which stores facts and concepts. Paris is the capital of France.
Got it.
And finally, episodic memory, EM, for specific personal events. I saw the Eiffel Tower last summer.
Okay, we have the components. Now, how does Karina use these memory stores to actually think and decide what to do next? What are its core cognitive activities?
Well, there are 4 key activities that really define the object level's intelligence. First is situation assessment. This takes input from perception, and it involves categorization and recognition.
So what am I looking at right now?
Exactly. Second is reasoning. This is the process of deduction and inference. It takes in existing beliefs, assumptions, expectations, all to reach mental conclusions, like refining a category or updating its internal knowledge.
So assessment identifies the situation, and reasoning figures out what that situation means given what it already knows.
You've got it. Third is problem solving. Given a goal, this module chooses and orders a sequence of actions, a plan, basically, to achieve that goal.
And then it all gets put into motion.
In the fourth activity, the overarching action cycle. This is the continuous loop that defines the agent's behavior. Decisions in Karina are often, they're associated with pattern recognition, combining that recognition and action in a really rapid recognize-act cycle.
That sounds like a continuous, very fast feedback loop. If the agent makes a plan, how does it know if the plan is working?
It's constantly monitoring. Monitoring the execution of a plan leads the system to constantly revise its estimates of the world state and, potentially decide on a whole new course of action. It's an extremely fast, resource-intensive cycle.
That's the object level, the part that gets things done. But the real advanced intelligence, the self-awareness, that's in the meta level, if the object level is the doer.
The meta level is the supervisor. That's a good analogy. The meta level takes the object level's cognitive task as its input, and it's dedicated entirely to introspection, to reasoning about the reasoning process itself.
So how does an AI look inside its own head? What does that introspective monitoring look like?
It generates self-awareness through 4 steps. First, profile generation. It reads the reasoning trace, the computation data from the object level.
Like reading its own log file.
Basically, yeah. Second, failure detection. It compares its current observations to what it expected based on its internal self-model. If there's a mismatch, say, it expected to categorize something and failed. That's a detected failure.
Okay, and then it has to figure out why.
That's step 3, failure explanation. It goes back to the reasoning trace to generate a causal explanation for the failure. Did it run out of time? Was the input ambiguous? Was the plan itself just bad?
Yeah, that's a critical step. It needs to know why it failed before it can fix it, right?
Right. Precisely. And that explanation feeds directly into the 4th step, goal generation. Once it knows why it failed, it generates a new goal, maybe to gather more information or to change the constraints of the problem.
And goal generation leads to meta-level control, the self-regulation part. So if introspective monitoring says, you're failing because you ran out of processing time, what does the controller actually do?
The controller uses a decision function to produce a really sophisticated control action. And this action is the system's ability to fundamentally change its own behavior or structure.
These aren't just simple commands.
Not at all. They can range from simple things like abort task, pause task, or resume task to more complex interventions like run task or, most powerfully, restructure task.
Restructuring a task. That implies changing the fundamental approach. If the agent realizes it's trying to solve a planning problem using only procedural memory, it might restructure the task to do a deep search of its semantic memory, right?
Exactly. It can change its resource allocation, its priority weighting, even the algorithm it's using, all based on its own self-diagnosis. That capacity for self-modification is what defines a robust cognitive architecture.
And the sources gave us a great implied example of this. The instructional planner agent in an intelligent tutoring system called FUNPRO. How does Karina manage a student's learning?
Right. So in FUNPRO, the agent's object-level task is to generate and execute instructional plans for a student, a sequence of lessons. The meta level is constantly monitoring the student's performance. If the student keeps performing poorly, the meta level detects that failure.
Which triggers the introspective loop.
Right. It generates an explanation. Why is the student failing? Maybe the prerequisite knowledge that the plan assumed just wasn't there. That explanation generates a new goal. The current plan is invalid.
And so the mid-level controller steps in.
It issues a control action, probably to restructure task, which leads to the generation of a totally new instructional plan. Maybe one that goes back to basics or changes the teaching style completely.
That ability to pause, reflect, diagnose, and fundamentally change strategy is why metacognition is so critical to AI. It takes the agent out of that rapid, sometimes flawed, recognize-act loop.
It's the difference between blindly executing code and genuinely understanding one's own capabilities and limitations. It's what we try to teach students, and it's what cognitive architectures are attempting to emulate.
Okay, so we've established that working memory is crucial in computational blueprints like Karina. It's in the nexus connecting everything. But when we transition from that clean, hierarchical structure of Karina to the human mind, the concept of WM becomes incredibly messy.
It really is the contested center of cognitive science. WM is generally defined as the workspace or blackboard of the mind, where active processing and temporary storage of task-relevant information happens.
The bridge between what we see and what we do.
The complex bridge, yeah, between sensory input and the decision-making processes tied to our long-term knowledge. But the first stumbling block is the very definition. Is it functional or is it mechanistic?
Can you clarify that distinction, maybe with an example, like remembering a phone number?
Absolutely. So you're looking up a phone number and mentally rehearsing it. WM can be defined functionally by what it does. It's any mechanism that helps with the temporary availability of that number. It just focuses on the observable behavior.
Okay.
The mechanistic definition, on the other hand, focuses on how the job gets done, the specific cognitive structures and mechanisms responsible. So is that phone number held in a dedicated sound-based buffer, or is it just highly activated long-term knowledge? That's the mechanistic debate.
That makes sense. And the classical, highly influential mechanistic view is the multi-component model from Baddeley and Hitch. How do they structure this workspace?
The Baddeley-Hitch model sees WM as a system of interacting components, not one single thing. At the top, you have the central executive,
The attentional control system.
the one responsible for supervising, planning, decision-making, and supporting the executive are two specialized subsidiary storage systems.
The famous two loops, phonological and visuospatial.
Exactly. The phonological loop is for temporary storage and rehearsal of sound-based material, like that phone number. And it's even further broken down into a passive store that holds the sounds and an active rehearsal system.
The mental subvocal speech.
The subvocal speech, yeah. The mechanism that refreshes the decaying trace. And this is seen as crucial in, say, natural language acquisition.
And the other loop.
The visuospatial sketchpad. It's specialized for the temporary storage of visual and spatial information, shape, color, location, all that.
This sounds like a perfect modular design for an AI. What evidence convinced researchers that these components were truly separate?
The key evidence is neuropsychological dissociation. The model relies heavily on studies of individuals with brain damage. If you find a patient whose brain injury selectively impairs their ability to maintain visuospatial information.
So they can't follow a path visually.
Right. But their ability to recall spoken sequences, the phonological loop, is perfectly intact. That strongly supports the idea that the sketchpad is a distinct, separable subsystem.
But a critical weakness often leveled against this model is how it handles the interaction with long-term memory. For instance, chunking. When I hear a string of letters, I don't hear 15 individual sounds. I hear 3 5-letter words. That's all LTM.
You've hit on the key challenge. The multi-component view acknowledges that LTM influences performance greatly. Chunking is a perfect example. To address this, Baddeley later added a third subsystem, the episodic buffer.
What does the episodic buffer do?
It acts as this temporary, multidimensional store that can integrate and bind information from the phonological loop, the visuospatial sketchpad, and, crucially, from LTM. It's the interface that allows for the storage of that kind of integrated information.
But even with that addition, this camp asserts that just saying WM is activated LTM isn't helpful.
It's unhelpful for detailed mechanistic research, they'd argue, because it doesn't specify how that activation and storage are managed. And that assertion brings us directly to the competing school of thought, Cowan's embedded processes model.
Right. Cowan's model takes that activated LTM idea and makes it the centerpiece.
It does. It suggests WM is not a separate storage system with dedicated boxes. Instead, it's an ensemble of mechanisms that keep information temporarily available. It proposes this strict hierarchy of activation within the existing LTM structure.
Okay, let's break down that hierarchy. What are the levels?
At the base, you have long-term memory, LTM, the huge dormant reservoir of all your knowledge. Above that is activated LTM. This is a subset of LTM that's temporarily activated, making it available for processing.
And items in there can interfere with each other.
Based on feature similarity, yeah. If you activate too many red objects, they start to kind of bleed together.
So if I think about a green apple, it's activated LTM. But if I try to actively manipulate that apple, say, rotate it in my mind, that happens at the top level.
Exactly. That rotation occurs in the top layer, the focus of attention, or FOA. The FOA is the highly limited subset of activated LTM. We're talking about 3 or 4 unconnected items where active, controlled, effortful processing takes place. It's often seen as the seat of conscious awareness.
And that's a fundamental difference from Baddeley. The limit isn't about running out of space in a box. It's about how many things you can actively focus on.
You've got it. And that brings us to the computational models, which muddy the water even more by defining capacity not by activation or structure, but by resource allocation.
Let's look at the ACTR architecture.
ACTR, which is one of the most comprehensive theories of cognition, views WM mechanistically as a subset of all declarative memory. Its capacity is not defined by slots or loops, but by a fixed resource called source activation, or DO dollars.
How does that resource constraint play out?
Think of DO dollars as the total fixed amount of attention bandwidth you have, like a limited internet connection. This resource is focused on the current goals. If you're doing one simple task, all the bandwidth can go to one goal node.
But if you have more goals streaming video, the bandwidth has to be shared.
Precisely. Dollar must be spread thinner across those goals. And when it's diluted, it has a smaller effect on the accessibility of related memory. It doesn't cause a hard failure, it just causes a gradual degradation of performance because the traces are less strongly activated.
So capacity is about the thickness of the attention spread, not the number of slots. That's a powerful shift. What about the time-based resource sharing model, or TBRS? That adds time as the main enemy.
Right. TBRS focuses on the idea that maintenance requires continuous attention. Its core principle is that temporal decay happens when your attention is diverted by other activities. When your attention shifts, the information you were holding starts to fade, and fast.
So if I'm trying to remember a list of names and someone interrupts me with a complex question, the distraction accelerates the decay. How do we fight that in the TBRS model?
For verbal info, TBRS suggests 2 additive, non-interacting maintenance mechanisms. The first is attentional refreshing. This requires attention and can refresh degraded traces during short pauses.
A general mechanism.
A general attention-based mechanism. The second is the articulatory loop, which is domain-specific. It holds the motor programs for speech, and like in the Baddeley model, it's limited to a very short duration, maybe 4 letters.
The fact that they're additive suggests we use both simultaneously.
Correct. But the total capacity is still limited by the need for attention. And finally, you have the Interacting Cognitive Subsystems Framework, or ICS, which kind of radically challenges the idea of a central resource altogether.
If they argue against a unified central executive, where does control come from, and where are the limits?
The ICS framework suggests that the idea of a single central executive is misleading. Instead, executive functions, control, planning, regulation, they just emerge from the complex interactions between specialized processing subsystems.
And the limits emerge from that interaction, too.
Exactly. Capacity limitations arise out of restrictions on the interfunctioning of these processes, not a specific storage limit or a single resource pool. So to sum up, we have 3 really different ways of looking at this. The dedicated modules of Baddeley, the nested activation of Cowan, and the capacity limits based on resources and interaction from the computational models.
It's clear why the field is so dynamic. They're all explaining parts of the same elephant.
The mechanistic debate we just covered leads us directly into the biggest mystery surrounding W7, the nature of its capacity limitation. Is it a fixed quantity, or is it a flexible resource we distribute?
The public imagination, and a lot of early research, really favored the fixed capacity idea, the magic number 7 plus or minus 2. But modern research often points to a much smaller number.
That's right. Behaviorally, in tasks like visual change detection, accuracy just plummets after 3 or 4 items. This provides really compelling support for a fixed limit, a set number of slots.
But the variable precision, or resource pool camp, has equally compelling data. How do they explain that drop in accuracy without using slots?
They argue the data can be fitted by models that assume you store all the items, but with highly variable precision. Think of it like this. Instead of having three fixed high-resolution cameras, the slots, you have one limited pool of electricity that powers all the cameras.
Ah, okay.
If you try to run 10 cameras, that pool of electricity, the resource, is distributed flexibly, making all 10 images low-res and really prone to error. The limit is about high-resolution processing power, not running out of storage space.
So whether it's fixed slots or a flexible pool, the system is fundamentally constrained. And that constraint makes the contents of WM incredibly vulnerable to interference.
Absolutely. Interference is seen as a primary mechanism of information loss. The fundamental trade-off is this. To be highly accessible, a memory representation needs high activation. But high activation also makes it more susceptible to interference, especially from subsequent things with similar features.
So interference both from old info getting in the way and new info overwriting the old is a major cause of forgetting.
A recognized cause, yes. And this vulnerability is what leads us to the crucial link between working memory capacity, WMC, and general fluid intelligence, or GRIF. Why is WMC such a powerful predictor of cognitive ability?
To measure WMC accurately for this, researchers use complex span tasks. Right? They don't just ask you to store info. They demand storage and processing at the same time.
That's the key. A classic example is the operation span task. You might be shown a word you need to remember, but right after, you have to solve a demanding math equation.
Oh, wow.
Yeah, like $4 times 3 plus 2 equals 14.4. Then another word, another equation. You're forced to use your executive system to maintain the words while simultaneously processing and inhibiting the distracting math problems.
That makes perfect sense. And the correlation exists because these complex span scores correlate so highly with general fluid intelligence. But here's where the sources get really interesting, challenging that initial assumption that this means smarter people just have bigger memory buffers.
That's the critical paradigm shift. Initially, researchers did hypothesize that GRIF was high because WMC's storage capacity was high. But the evidence now strongly suggests that the correlation is not primarily due to storage capacity causally influencing GRIF.
Why not? What are the holes in that bigger buffer theory?
A few things. First, if storage capacity were the key, then more complex reasoning problems should correlate more strongly with WMC measures than simpler problems. They don't.
Interesting.
The correlation stays about the same, which suggests the underlying mechanism isn't storage quantity. Second, attempts to improve GRIF by intensively training WMC, just giving people practice on span tasks, have largely failed. People get better at the specific task, but the benefit rarely transfers to broader GRIF measures.
So if it's not the sheer size of the memory, what is the common denominator? What's the thing that links WMC performance to fluid intelligence?
The link is mediated by executive attention control. WMC, especially as measured by these complex span tasks, reflects the ability to apply activation to memory representations, to bring them into focus and maintain them, especially in the face of interference or distraction.
So intelligence in this context is defined by the quality of the manager, not the size of the warehouse.
That's precisely.
Right.
Executive attention control coordinates two critical and often competing functions. The first is maintenance, the ability to keep goal-relevant items active and available.
And the second?
The second, and arguably more differentiating function, is disengagement or inhibition, the ability to actively suppress, block, or remove goal-irrelevant or outdated information. This is crucial for managing proactive interference.
So when you finish one task and start another, you have to actively block the irrelevant data from the first one.
Exactly. The more flexibly and rapidly you can control this attention, the better you perform on GRIF tasks. This makes the ability to forget, or at least to ignore, a highly active, controlled cognitive process, not just a passive failure.
It's the true measure of cognitive control.
It is. The ability to dynamically and flexibly control attention to manage the flow of relevant and irrelevant data under time pressure is the core mechanism that explains the relationship with GRIF. The amount of available processing resources for executive control, not static storage capacity, is what really counts.
That's the secret sauce of complex thought, isn't having more memory, but having better, faster, and more flexible control over the memory you already possess.
When we focus so much on the limits of WMC and executive control, we run the risk of seeing WM as this separate, isolated system. But there's a strong consensus now in cognitive science. Long-term knowledge and skills play an integral role in WM performance. You just can't understand WM without considering LTM interaction.
This confirms the hypothesis from Cowan's model that WM is just activated LTM, but now we can define the specific measurable ways that LTM provides support. What are the primary mechanisms?
There are three main ways. First, chunking skills. LTM provides pre-existing knowledge units, words, acronyms, known objects that are bound together in WM. Acquiring these skills allows experts to dramatically compress information, effectively expanding their functional memory span.
Okay, that's chunking. What's the second?
Second is redintegration. This is a reconstructive process. If a memory trace in WM fades or gets partially degraded.
Like you only remember the first and last sound of a word.
Exactly. Semantic LTM helps to disambiguate and reconstruct the missing pieces, allowing for more successful recall than you'd have otherwise. It's like a safety net.
A safety net that helps stabilize decaying information. What about the third mechanism? Long-term working memory, or LTWM. That term still sounds like a contradiction.
LTWM, which was proposed by researchers studying experts like chess masters, addresses how individuals can operate with massive amounts of information without violating that strict 3-4 item limit of the attentional focus. It uses specialized LTM retrieval structures. These are highly organized schemas that allow the expert to efficiently encode, store, and retrieve information relevant to their domain, often by using just 1 or 2 items in the focus of attention to index these vast LTM networks.
Let's look at the classic case study that demonstrates this. SF, the digit span expert.
Right. SF was famously trained to have exceptional digit span, eventually recalling over 80 digits. But crucially, his general WMC did not increase. His success came entirely from acquiring specialized encoding processes.
He used LTM retrieval structures.
Yes, to group digit sequences into known units like running times. So he wasn't remembering 80 numbers, he was remembering maybe 10 running times.
And the chess grandmasters provide an even more compelling demonstration of this dependency on domain structure.
They're the canonical example of LTWM. They maintain the positions of pieces across 10 or more simultaneous blindfold games, relying on their vast LTM knowledge of game patterns. But if you test their memory for chess positions where the pieces have been randomly rearranged, their memory span just collapses back to about 5 pieces, the level of a novice.
That's a stunning illustration. The only difference is the availability of meaningful long-term structure.
It's core evidence that LTWM relies entirely on domain structure provided by LTM. This leads to the circumvention of limits hypothesis, the idea that intensive training and domain-specific knowledge might overcome or even eliminate the fundamental limitations of WMC.
But the sources suggest this hypothesis is generally refuted by the data, right? High knowledge doesn't make fundamental capacity limits irrelevant.
That's correct. Studies consistently show that domain-specific knowledge and WMC effects are usually additive. For example, in a study on memory for a baseball game, researchers found that both a participant's WMC score and their deep baseball knowledge independently predicted their memory performance.
So one helps, but it doesn't cancel out the other.
Exactly. A high level of knowledge helps performance overall, but it does not eliminate the effect of individual differences in WMC. So even the greatest expert still has to deal with the same attentional constraints as the beginner. They just package the input far more efficiently.
And LTM goes beyond just packaging information. It fundamentally changes how we interact with the environment, right? Directing attention before information even hits WM.
Precisely. The study involving burglars looking at apartment photos demonstrated this perfectly. The burglars, because of their specialized LTM, noticed significantly more burglary-relevant features, locks, windows, access points, than a control group of homeowners.
So their expertise acts as a filter.
It prioritizes certain environmental cues, directing attention based on LTM schemas, and ensuring the most relevant information is the first to be selected for activation in WM. So memory isn't a passive reception device. It's an active process of filtering the world based on what we already know.
We've moved from the computational blueprint to the psychological models and the crucial role of LTM. Now we have to turn to the brain itself. Where did these abstract concepts, the control, the focus, the resources, actually reside in the wetware?
The latest neuroscientific evidence is deeply consequential, and it's pushing us away from that classic idea of WM being a single, separate, dedicated memory system.
What's the new view?
Instead, WM functions are increasingly viewed as emergent properties of systems that already exist for sensory processing, attention control, and action. It's a less of a distinct WM box and more of a synchronized functional state across multiple regions.
Which regions are driving this state, particularly the maintenance and control aspects?
The prefrontal cortex, the PFC, is absolutely crucial. Its role is to maintain goal-relevant representations in a highly active state. Neurological damage to the PFC results in profound impairment in central executive functions, maintenance, organization, planning.
But not a loss of general awareness.
Generally not, which reinforces the idea that the PFC is the primary control system.
We talked about the computational need for a gate, a mechanism that protects current WM contents from being interfered with. Does the PFC have a biological gate?
It appears so, and it seems to involve neurotransmitters. The source material suggests that dopamine, or DA, may implement a sophisticated gating function in the PFC. When the gate is closed, PFC representations are protected from interference, allowing the system to maintain a stable focus.
And when it opens?
New information can be rapidly updated. This gating mechanism is believed to augment the computational power of the PFC network, protecting the current focus from overwhelming context or automatic interfering retrieval from LTM.
The very interference we talked about is a major cause of performance decline. It's like a bouncer at the WM club.
That's a great analogy. Beyond the PFC, what about the hippocampus? We usually associate that with LTM formation.
Does it play a role in complex working memory?
Research suggests it does, particularly in performing complex WM tasks that require binding, especially in early learning. Its function seems related to facilitating the temporary binding of multiple representations that need to be held together, say, linking a location, a color, and a task goal.
Okay, let's pivot back to the focus of attention, the FOA. Psychologically, we debated if it was a single limited resource. Does the neuroscience support a monolithic view?
Quite the opposite. Growing evidence suggests the focus of attention is manifold. It's compilation of multiple distinct processes operating in concert. We have compelling, direct evidence from studies using EEG, which is excellent at tracking rapid, real-time brain activity.
And this evidence revealed two distinct neural indices tracking different subcomponent processes. This is a crucial finding. Let's break down the two signals.
The first is the contralateral delay activity, or CDA. This signal tracks the number of item-based representations, the individuation and detail encoding of distinct objects.
That's sensitive to mnemonic load.
Very sensitive. If you asked a subject to remember 2 squares, the CDA is low. 4 squares, the CDA increases proportionally. It tracks the stuff we are holding in focus.
The objects themselves. What does the second index track?
The second is alpha power lateralization. This tracks currently prioritized spatial locations, or the spatial index. In studies where participants were cued to attend to a location but not necessarily encode the item details, alpha power showed significant lateralization, but the CDA was muted.
That is a phenomenal dissociation.
Yeah.
The brain is literally using different neural signatures to track where attention is focused versus how many things it is individually maintaining.
It provides strong support for the non-unitary view of the immediate workspace. If the focus were monolithic, these indices would rise and fall together.
Finally, let's discuss the highly advanced finding on how the cortex physically manages priority changes to protect memory, this idea of priority-based remapping.
It is truly cutting edge. This research uses techniques like inverted encoding modeling, or IEM, which is a sophisticated way to decode what neural activity is representing. These analyses suggest that when the priority of a WM item changes,
Say an external cue signals a previously irrelevant item is now the target.
right, when that happens, the neural representation of that item is literally rotated or remapped into an orthogonal dimension within the representational space of the cortex.
That sounds like changing the address of the data in the brain. Why would the system do that?
This rotational dynamic is hypothesized to be a general computational principle by which the cortex protects memories of prior events from catastrophic interference by incoming stimuli.
It's like instantly moving a crucial file into a hidden protected folder before some new program can overwrite it.
That's the ultimate mechanism of attention control. It's physically isolating the relevant information by changing its neural coordinate system to ensure a coherent and focused thread of cognition. The brain is prioritizing robustness over ease of access.
And that robustness is essential because, as we saw with ACPR and TBRS, cognitive systems are resource-limited and highly susceptible to decay and interference.
The brain has evolved powerful, dynamic mechanisms to actively fight that vulnerability.
We've concluded an extraordinary deep dive, moving from the clean logic of computational blueprints to the contested yet functional dynamism of the human memory system. We started with Karina, seeing how an ideal intelligent system needs those dual layers of control.
The object level for execution and the meta level for self-diagnosis and strategy restructuring.
And we solidified the idea that the heart of intelligence, whether artificial or biological, is the management of working memory. The trend is undeniably shifting from viewing WM as a simple storage chip to seeing it as a dynamic, coordinated system of attention and activated long-term knowledge.
Absolutely. Fundamentally mediated by control mechanisms. Whether we prefer the multi-component view, Cowan's hierarchy, or the resource allocation constraints of the computational models, the recurring challenge is always the same.
How to manage information flow, prevent decay, and most importantly, control interference.
The neuroscience corroborated this control-centric view perfectly. It established that the link between WMC and fluid intelligence is primarily driven by executive attention control, the ability to keep goals active while suppressing powerful distractors.
And that the focus of attention isn't monolithic, but is dynamically tracked by these dissociable neural indices for location and item detail.
Right. We've seen that true knowledge and expertise aren't just about having more information stored, but about acquiring specialized encoding processes that let us package information efficiently, transforming the quality of our input.
And this brings us back to those cutting-edge neural findings on memory protection. The most sophisticated neural mechanism for managing memory prioritizes the protection of prior, goal-relevant information by literally changing the neural code.
Rotating representations into an orthogonal dimension to shield them from incoming interfering context.
So, given that the biological architecture seems engineered specifically to isolate and protect our immediate focus by dynamically changing the neural landscape, we have to ask, how much of our everyday forgetfulness, losing the thread of a conversation, or forgetting a fact the moment a new one is introduced, is not actually a failure of storage,
but instead a success of the system? A success of the system dynamically protecting our current focus from overwhelming context.
That's a marvelous thought. It means our cognitive limits are less about what we can't hold and more about what the system actively and successfully manages to ignore to keep us focused on the task at hand.
That is definitely something worth pondering on your next deep dive.
A perfect place to leave our deep dive for today. Thank you for guiding us through these computational and cognitive blueprints of the mind.